So what we're going to do now, I need to go back a little bit, almost passed up something called grounding. So grounding a circuit, that shouldn't take too long to explain. And then we're going to jump into power. Okay. And I have a little simulation to show you with an RC circuit. So let's jump into the grounded circuit first. All right, so for grounded circuits, let me set up, I don't know, some circuit. We're not going to analyze it. I just want to show you what grounding does. Okay, so remember what I showed you guys last before the break, that you have a certain voltage here, and then you go to a resistor. That resistor causes a voltage drop here, and then you have another voltage drop here. Okay, so what the ground does, once you attach a ground, let's say I'm going to attach a ground here. Wait, let me do that in black. It's part of the circuit. Okay, so there's a ground, and what the ground does is essentially gives you a reference point for your voltage. Pretty much anything connected to this ground, you're going to get a 0 voltage. Okay, so I could have put the ground there, I could have put the ground here, and this would have become 0. I could have made it here, and this would have become 0. So it makes everything measured, this whole circuit will be based off where this ground is. So if this is 0 volts, then because this battery is, let's just give it a number here so I could reference it. Let's say this is a 10-volt battery. Okay, so if this is 0 volts here, then the blue one would have been 10 volts, right? Because they have a voltage gain here. So it just gives you a reference for your voltages. As far as safety goes, any excess current, any surge in current, the ground will take care of that. The ground, so all this, if there's like I don't know, something happened here where it shot up more voltage, like it jumped up in voltage for whatever reason, and all of a sudden you have all this current here, all the excess voltage will go down to the ground. And the reason why it goes down to the ground is because the earth will take those electrons. There's no repulsion from the earth to those electrons. So it becomes really important for safety. So like let me just draw a quick picture here. Actually, do I have it? I might have it up in my PowerPoint I could share with you guys. Oh yeah, here. All right, so this is where it becomes really important for safety. So this is what current would want to. Current does want to go to the ground. So it would use, so you have a 120 volt source here. Let me get this pointer. You have a 120 volt source here. That 120 volts is going to send current, and let's say this guy's holding this wire for some reason. He's holding the current, and the current's going to want to go back to the ground, right? And you kind of see this here. If this is not, you can kind of see there's no GFI here. There's no surge protection here. So this person's touching this hair dryer, and it's not properly grounded. It could shock this person, because any non-grounded current that might be resting on the surface of this could go through, and will go through her and go down and to the faucet here. Okay, so we don't want that to happen. So here's kind of another picture. This is the way it's supposed to work, right? You have current going in, goes into your microwave or whatever it is, and comes out. But there is a possibility that this wire is shorted out or is touching the casing. And if you touch that microwave or whatever it is, if you touch that box, the current wants to go to the ground. So it's going to use you as a wire to get down to the ground. Okay, that's why if we put a ground here, grounding, that's how we say it, grounding this box, any excess current here, well, instead of going to your hand, will go down to the ground using this wire. Okay, and perhaps you heard this, a current will go the path of least resistance. Our bodies have a resistance of, well, it's in the order of mega ohms, okay, for typical resistance. So it's not, you might get a little current running through us, but most of the currents is going to go through to the ground. Okay, so safety issue there. Really good to remember as you're grounding things. Okay, well, stop there. All right, so that's all I wanted to say about ground. I'm gonna go back to the whiteboard here. Okay, so that's all I want to say about ground, is that not only does it give you a reference point for your voltage, but it also makes sure that no excess current goes, to you, which is always a good thing. All right, so let's go to power. All right, so to talk about power, well, we know the units for power. Let me start there. Units for power, joules per second, which we say is a watts. Okay, so it's essentially how much energy, if we're going to put it in the context of circuits, how much energy is flowing through the wire, or is being, we would say, dissipated by a resistor, right? The resistor heats up, and that energy or that heat is lost to the surrounding, so it loses energy to the surrounding. How much heat is dissipated by the resistor? Okay, so we're going to start with this basic kind of definition of power. Power is your change in energy over time. Okay, change in energy over change in time there. So remember the du just means a small, infinitesimally small change of energy, and over a very small change of time. Okay, if we're talking about charges, what we're looking at in energy is QV over dt. Okay, so that energy, where does that energy come from? Well, it comes from the voltage change that these charges undergo. Okay, now if we're talking about something like I have up here, like this circuit here, the batteries is supposed to maintain a constant voltage here, right? So V doesn't change, but the Q does, right? Where a current is this flow of charge here. So I have my Qs are changing. I have Qs flowing through this wire. So I'm gonna put this as, whoops, let me rewrite this. Okay, so V comes out there because it's a constant. And I have dq over dt. What's dq over dt? Like charge over time? Well, that's just currents. Okay, so we could find out power pretty easily by doing current times voltage there. Okay, so another way we could visualize where this power is coming from. If you let me draw this out really quick. Let's say we have this resistor here, and of course we have the electrons going in from this direction. Let's just say it's coming in from this direction, right, with a certain velocity. And this resistor has certain length L. Okay, so there is an energy loss. As this electron goes through this resistor, there is an energy loss there, which I call this delta U for energy. I would use delta E, but then E is electric field. So let me just stick with U for representing energy. Okay, so there is an energy loss there associated to the work done on this charge as it moves through this resistor. Right, so I'm gonna put this as FD here. Right, that's work, right? Force times distance. And force times distance. Well, what force are we talking about? It's a force. Well, we're looking at the force from an electric field. Forces from electric field is QE. And the distance here is the length of that resistor, right? That force acts on that capacitor, acts on the charge as the charge flows through the resistor. So I'm gonna call this L here. Okay, and if I look at, let me rearrange this a little bit. Okay, electric field times distance, right? E times L. Well, we all said in, what chapter was that? Chapter, I think it was chapter 26, that this is equal to your change in voltage. All right, so that gives us another way of finding, right? We get back to that Q times delta V, but just from a different perspective there, right? From the perspective of work. Okay. So we essentially get the same thing, right? If we want to see what is the change of energy over change in time, right, we're essentially doing what we just did previously, right? And that gives us the same result, that your power loss in this resistor equals your current times voltage. So it's just a different way of getting to the same point there. Okay, so if we're talking about a resistor, this is how much energy is, let's say, is transferred to the resistor as a resistor heats up. Like I said, it's called dissipated energy. It's how much energy per second, right? Because we're talking about power. How much energy per second is lost through this resistor. Okay, so there's a couple other things I could do with power. If we use Ohm's law, so remember Ohm's law, V equals IR. All right, we could get a couple of other equations for power. We could get, let me put this in a different color. So it's just making some algebraic substitutions, right? For instead of I times V, let's substitute in for I using Ohm's law, and you get V squared over R. That's one way of finding power. Or let's substitute in for V in this equation. Right, if I use this equation, substitute in for V, I get a different equation for power, I squared times R. Okay. Okay, so that is the our power, how we calculate power going through a resistor there. So maybe we could do one example. Let's see here. Let's do, oh, I know. We'll do a simple, because we already did some pretty difficult examples with circuits. So I'm gonna do a simple example just so we could get this calculus power, and also introduce to you a real battery. I don't think we've done yet. Okay, so so far we said when we talk about batteries, we were saying an ideal battery maintains its voltage, or we call it an EMF, right? Okay, so that's for an ideal battery. Now, batteries are not ideal. They don't maintain voltage. Real batteries have an internal resistance. Which decreases the voltage of the battery with more current flowing through the battery. I'll show you what I mean. Okay, so if we're looking at a battery, the more current you put to the battery, the smaller that voltage of that battery is going to become. Let me show you why. So I'm going to have a simple circuit here. Let's see here. so this is my battery right here, and let's say this battery is connected to a resistor. All right, it's my battery. All right, in a real battery, inside that battery, you have the EMF, right? The thing that's causing or that's giving you your voltage, right? And that has to do with a chemical process that goes inside, that goes on inside a battery. Okay, you have this EMF and an internal resistance, right? So that internal resistance might be due to some kind of corrosion, something there that is prohibiting that internal resistance. So we're going to model that internal resistance as just its own resistor, and I will call this lowercase I RN. Okay, the RIN, it represents internal resistance. Okay, and then the voltage down here I'll call EMF. Okay, so this battery, inside this battery has an EMF, right, which gives you a voltage gain, and it has an internal resistance, which gives you a voltage drop. So if I really wanted to know what is the voltage of the whole battery, not just the EMF, but the voltage of this whole battery right here, I would need to consider the voltage gain from the EMF and the voltage drop from my internal resistance. Okay, so I'll rewrite it, write the voltage of the battery like this. Voltage of the battery is going to be the voltage gain from the EMF minus that voltage from my internal resistance. And if I use Ohm's law here, that voltage from the internal resistance is going to be equal to I RN. Okay, so that tells me as current goes up, as I put more current through the circuit, right, I goes up, and if I goes up, the voltage of my battery decreases here. Okay, so that's how real batteries work. The internal resistance is not going to keep, let's say it's a 1.5 volt battery. The more current you're demanding from that 1.5 volt battery, the less voltage you're actually going to get because of this internal resistance here. Okay, so I want to define power. So let's say we have a resistor. Actually, I think I have this problem in my PowerPoint. Let's see. I thought I didn't see it. Oh, here it is. Okay, so let me show you guys. All right, so this is what I want to do. A battery whose EMF is 12 volts is connected to a 65 ohm battery, 65 ohm resistor, and the current which runs through the resistor is 0.1833 amps. Okay, so we're actually, I want to include something else in here. So what is the voltage across that battery? That's not going to be too hard to figure out. We'll do it really quick. And then what is the internal resistance? And I want to add another question here. What is the power loss by that internal resistance? Okay, what is the power loss by that internal resistance? So we're going to answer those questions here. Try to answer on the slide. If I run out of space on the slide, we'll go over to the whiteboard. All right, so the circuit is really similar to what I just drew. You have your battery. Here's your battery. And you have the resistor. So I'll draw a little kind of dashed line here for my battery. Okay, so all that's inside my battery. You have your EMF in the battery and the internal resistance of the battery. So what we're told is that the EMF of this battery is 12 volts. So that 12 volts is referring to this part right here. This part right here. The resistor is connected, this battery, this whole battery, is connected to 65 ohm resistor. So that's this resistor here. So, oops, I wanted it in white. Okay, so and it tells me the current that runs through the resistor. I'll do that in red. So this current is 0.183 amps. Okay, so what is the voltage across the battery? So voltage across the battery is not too hard. Voltage across the battery just equals current times resistance, right? So the current going through that battery is 0.183. Oh, sorry, the current going through that resistor, I should say. 0.183, and the resistance 65. So I can figure out what that voltage is pretty easily. 0.183 times 65 gives me 11.9 if I keep it at 2 sig figs. Okay, now that 11.9 is important, right? That 11.9 volts is my voltage across my resistor, but remember this is all in, they're connected together. If you go around the loop, right, your total voltage is 0. So if this is 11.9 volt drop, that's telling me my battery has an 11.9 volt gain, right? The whole battery does, not just EMF, but the whole battery. Okay, so let me make that a note of that. Okay, this is V battery as well. Okay, so if that's V battery, looking at, and the question is, what is the internal resistance here? Well, we know from what I had in the previous slide, V battery equals your EMF minus I times Rn. Okay, so we just calculate V battery. 11 points, and I'll keep one extra sig fig for my calculator. I guess it'll be the same thing. I'm gonna keep a couple extra. 895 volts. So that's the 11.9. I'm just keeping extra sig figs. My EMF is 12.0. My current running through this was also given to us 0.183, and then we have RIN. Okay. So just a matter of doing some algebra here to find the resistance. You do the algebra and you get an internal resistance, and this is kind of typical for internal resistance, pretty small. I get 0.57. Is that right? 0.574. Oh, not amps, ohms. Okay. So I use where that V battery equation come from. This is what I just talked about earlier, right? On the whiteboard, right here. Oops. I used this equation here, right, or down here, and applied it to my problem, here. This is just the voltage across the battery. Okay, so I did want to do one more thing, and that is calculate the power by that battery. So the power, not by the battery, was the power lost by the internal resistance. So probably it would be easiest to, you have all those equations to use. Probably easiest to do I squared times R, where I is a 0.183, and the R is your internal resistance, so 0.574. Okay, so calculate the power just by that. So 1.83 squared times your resistor, your internal resistance. You get pretty small. I get 19.2 millijoules. No, not millijoules, milliwatts, I should say, because we're talking about power. Milliwatts. Okay, so yeah, internal resistance, pretty small value and pretty small resistance. And because it's a small resistor, it usually doesn't take a whole lot of power, right, away from your circuit. Right, so it's losing 19.2 millijoules a second, which is right, which is why we write 19.2 milliwatts. All right, good. Don't be afraid to ask me a question during the lecture. I want to make sure that we are, or you guys are with me as I'm going through this. Okay, let's go to the last topic here, which is the RC circuit. RC circuit. So the RC circuit, let me show it to you. So I have this little simulation here that hopefully you guys can see on your screens. In that simulation, we have a couple things here. So let me describe what we have here, and I'll try to make it not so messy. Okay, so here's my circuit right here. You guys can see my mouse, right? Let me know. Just give me like a thumbs up if you can see my mouse. Oh, yes. Okay, good. All right. So in this circuit, you get a battery. So that battery is providing the voltage. I have a switch there. I hope you guys played that game, Crack the Circuit, because I think that game does a good job about showing you what switches actually do. But you have a switch here and a capacitor. And if I close this switch, the capacitor and the light bulb will be connected together. So this is what I'm gonna do. I'm gonna connect this switch first. So I'm gonna close this switch. When I close this switch, keeping this one open, all I'm doing is connecting the battery to the capacitor. Okay, so and by the way, this is an ideal battery. It has no internal resistance. So if you see it catch on fire for a second, that's just because current went so high that it caught on fire. All right, so oh wait, nothing happens because I need to press play. There you go. Okay, so I'm gonna close this. All right, there we go. So what this battery did is it charged up this capacitor here, right? And I have this switch closed here, or open, so the light bulb is not part of the circuit yet. But the battery charged up this capacitor, and you can see, here's my voltmeter, right? Remember, a voltmeter measures voltage. So if I put this voltmeter on one side of the battery, and the lead on the other side, okay, it tells me 25 volts. If I do it for the capacitor, also 25 volts. Okay, so what this battery did was just charge up my capacitor to the same voltage. Okay, so I'm gonna open this, and there it's still 25 volts because that capacitor is maintaining that charge. Okay, let me show you what happens in the next one. So I'm gonna close the next switch here. Once I close that next switch, we're gonna start to see a discharge. All this charge is gonna, let's say this positive charges. All these positive charges are gonna, I guess I could do it. It's gonna flow to the light bulb, turning it on, but then going to the negative side and then neutralizing this side. I think actually what the animation shows is a motion of the electrons. So if I were going to do the motion of the electrons move from the negative plate, go through the light bulb, turning it on, and neutralize the positive plate. So let's see that. Okay, so there you go. You can see those charges moving, but look at the brightness of that light bulb. It's not staying as bright. Actually, I don't know if you guys could tell, but it's getting a little bit dimmer and dimmer and dimmer, and eventually it's going to reach 0. Okay, so this is called the RC circuit discharge. This is a capacitor, the C, and this is my resistor. And as I do this, we're essentially discharging this capacitor, but using the resistor as kind of controlling how fast that happens. The more resistance I have, the slower this is going to go, right? The slower discharging I get. Okay, so let me charge this back up. Boop, there you go. Okay, open this. And I want to show you what's happening to the voltage and the light bulb, across the light bulb, and I want to show you what's happening to the current. Okay, so right now it reads 0, it reads 0. Remember, this was at 25 volts, right? The capacitor was at 25 volts. Okay, and I'm going to do this step by step. So I'm going to close this. Nothing's going to happen because I press pause. And this button right here, that's going to let me go, you know, step by step rather than just press play. So if I press that, you can kind of see what happened there. Voltage jumped up. Jumped up to, oh, yeah, 25. Okay, so as soon as I connect this voltage across the capacitor equals the voltage on my light bulb. Now that voltage is going to go down, right? As this loses charge, voltage goes down, and the voltage of the capacitor goes down. So we're going to see that. You can see that voltage start to decrease, and same thing with the current. Current reached its maximum value here, right when I connected it. As soon as once I press play, that current starts to drop and start to decrease. Right, you can see that there. Okay, so RC circuit is a time-dependent circuit. How quickly it goes to 0 depends on two things. It depends on my resistance, right here. Depends on my resistance, and it depends on my capacitance. Right, the more charge I could hold, the more current I could give. The more resistance I have, the slower the more I could slow down that current. Okay, so that is an RC circuit. I want to, now that you guys see it, I want to analyze it and see what equations we get there. So let's go back to the whiteboard. Okay, so let me see. Let me draw the RC circuit. I'm just going to draw the C and the R of it. So here's my C, here's my R. I should draw a switch. Let me draw my switch right here. Okay, so here's the C and the R. Let's say this capacitor is charged, so let me put some charges here. So positive and a negative on the bottom. Okay, so this capacitor is charged up. As soon as I close that switch, okay, so let me put this here. Current begins to flow. Circuit. And we just saw in the simulation, this will be max. This will be the maximum current because that current is just going to start decreasing. So as soon as I close the switch, current starts to flow. This will be the maximum current. Let's actually calculate what that maximum current is. It's not too hard. If I do the loop law, right? Let's pick a loop. Oops. I'm gonna do a different color. Okay. So here's my loop. First, I have a voltage gain of my resistor. Sorry, my capacitor. First, I have a voltage gain as my capacitor. As I go this way, right, negative to positive, that's a voltage gain. I go around and I have a voltage drop from my resistor. And we know from the loop law that if you add up all the voltages around a circuit, you get 0. All right, so let me make a couple of substitutions here. Voltage across a capacitor. We're gonna go back a couple chapters, and we saw that this would be Q over C. And at this, we are looking at when I as soon as I close the switch, right? So as soon as I close the switch, I'm looking at maximum amount of charge. Okay, because it hasn't lost any charge. It's been charged up to its maximum value. And then substitution for VR. Okay. Okay, so this gives me my Imax. Imax equals, let's see, Qmax over RC. That's my Imax value. Okay, so what happens when we're not looking at maximum value? Well, this is where the time dependency comes in. And we have to be kind of careful here as far as how we do this. So I'm kind of running short on time, so I'll try to do this a little quicker here. Okay. What happens after you close the switch? Close the switch. In other words, after maximum values. So I know right when I close the switch, I'm going to get those maximum values, right? Maximum current and maximum charge, you know, all that's true. But just a moment after, what happens to the voltage, is the current? We know it's going to decrease because that's what we observed. So let me write this way. I'm going to write this, my equation that I have down here. This equation down here, I'm going to write it a little differently. I'm going to note that, you know, remember I is just dq over dt. Well, where is this q coming from? This q is coming from the loss of charge in the capacitor, right? The reason why you have current is because the capacitor is losing charge. I hope that makes sense. Okay, the reason why you have current flowing through the circuit is because the capacitor is losing that charge. So I'm going to relate this Q that I have up here to the Q of the capacitor, and it's going to be a negative. The reason why it's a negative is because that capacitor, or the charge of the capacitor, is decreasing. All right, so if I write my current like that, right, d capital Q over dt, or negative d capital Q over dt, and plug it back in, get this equation here, so dq over dt r equals 0. Okay, so we get this differential equation, which is not too hard to solve. This differential equation simplifies, and we could integrate. So again, I'm running low on time here, so I'm gonna kind of skip the algebra and say you could get this dq over q equals 1 over rc, or dt. I should have a negative there. Yeah, I have a negative in front of that dt. All right, so I should rearrange that algebraically to get dq over q equals negative dt over rc, and then I'm going to integrate. So I'm going to integrate from t0, for t equals 0, to some time t. I don't know, some time in the future after I close the switch. And then for my q's, I'm going to integrate from q max. Right, because that was a Q. When I closed the switch, I had Q max. So integrate from Q max to some charge at some later time, so Q. Okay, so we do that integral. The left side, we get, let's say, integral of 1 over Q dq gives me ln of Q from our Q max to Q. And on the right side, you take that integral, and that just becomes negative, well, yeah, negative t over rc from 0 to t. All right, so I'm just taking the integral on the left side and the right side. That's what I get. And then once we do that, it's just a matter of doing some algebra there, plugging in your limits. And this is what we get. We get an equation for Q. Q equals your Q max E to the minus T over RC. If you're confused about where that E came from, that exponential function, it came from the fact that I got rid of this ln, right? If you take E to both sides, the ln goes away. The E and the ln goes away. So a little kind of, may have to go back to your algebra days to see that, but I'm sure you guys remember that. Okay, so I get this, and oftentimes, it's kind of interesting. This RC is essentially determining, in this function, determines how rapid this exponential decay is, right? We get e to the negative t over RC. Depending on what RC is, will determine how rapid we lose our current, or sorry, we lose our charge. So because that's this RC, we kind of give it a special name. Okay, RC is known as the time constant. Okay, essentially after one time constant, let me put it, which is in units of seconds. Okay, so RC is in units of seconds. It tells you a time. After one time constant, let's see, let's forget the value. You have lost 60, let's see, it would be, doing a quick calculation there, 63% of the charge. Okay, so that's what this time constant is. And it's usually written like this. It's kind of a curvy T. Okay, so this is what I said earlier. Depending on what your resistance and your capacitance is, will determine how quickly you lose charge. The more resistance, the slower that discharge. Same thing with capacitance. The higher capacitance, the slower the discharge. Okay. All right, so this right here, if I applied this equation, right, Q over, just divide both sides by C, divide this side by C, divide this side by C, I get an equation for my voltage, which is what we observed. V equals V max e to the minus t over tau. Okay, so that showed us what we saw. Voltage decreases as a function of time, right, exponentially. And if I multiplied, or not multiplied, divide both sides by resistance, right? If I divide both sides here, divide this side by resistance and divide this side by resistance, I get an equation for current. E to the minus t over tau. It's supposed to be a minus there. Okay, so this explains what we saw earlier when we looked at that simulation I showed you guys. Voltage decreased exponentially, right? It reaches maximum and then decreased, and then current reaches maximum and then decreased. Okay, so that RC circuit, pretty important circuit. It comes up in a couple of different areas of life. Let me share with you this really quick as we wrap this up. So all those things uses some form of the RC circuit, right? The reason why is because it's a time dependency. So if you want to adjust how long that flash is on, right? You could change your resistance, you change your capacitance, and that will determine how long the flash goes on before the light bulb dims to zero. Same thing with the pacemaker, right? You want to adjust the timing of that pacemaker, you change the resistance and the capacitance. Okay, now they're not going to be all like straightforward RC circuits. You know, to get more complex, especially for something like a pacemaker, you want that to last a long time and to be reliable. But they all use kind of the same concept as what we just discussed. Okay, so that is an RC circuit. We didn't have time to go over charging a capacitor, which is kind of the inverse of what we just looked at, but it's really similar. The last section of chapter 28 discusses that, but essentially is what we did, kind of in reverse. So take a look at that to see how capacitors and resistors actually charge rather than discharge, but it's very, very similar. All right, so we're gonna end our, I'll go back to the whiteboard in case you guys want zero writing notes there. We're going to end our lecture here. We finished chapter 28 now. In our next lecture, we leave electronics for a bit, and then we're going to focus on magnetism. So we'll do that in our next lecture.